So imagine you're watching a state-of-the-art AI robot, right? It successfully navigates a kitchen, it opens a microwave, carefully places a hot dog inside, and then,
let me guess.
yeah, it immediately reaches back in, grabs the hot dog, and pulls it right back out.
Oh, man.
Welcome to AI Paper Slop. Today we are unpacking a brand new paper titled DexJoCo, a benchmark and toolkit for task-oriented dexterous manipulation on MuJoCo.
Which is a bit of a mouthful, I know.
It is, but it exposes exactly why our smartest AI models currently have, well, the physical memory of a goldfish. Let's get straight into the executive summary.
Right, so DexJoCo is basically this new simulation benchmark built within MuJoCo, and it's specifically engineered for multi-fingered, dexterous robotic hands.
Not just those simple claw grippers.
Exactly. The authors designed 11 highly complex tasks. We're talking tool use, bimanual coordination, long horizon execution, and reasoning tasks.
And they needed a ton of data for this, right?
Yeah, over 1.1K high-quality human demonstrations, and they collected all of this using a really clever, low-cost, smart glove teleoperation setup.
Which is huge for the engineers listening.
It really is. Then they threw the heavy hitters at this new benchmark, testing major vision language action models, or VLAs, like ACT, diffusion policy, Pi 0.5, and GR00TN 1.5.
And the core insight here is, it's a massive reality check. If you are an ML engineer working on VLAs or sim-to-real control pipelines, you need to hear this.
Definitely.
Because while models like Pi 0.5 actually showed some impressive robustness to severe dynamic randomizations, the benchmark laid bare some catastrophic failure modes.
Common ones, too, across the board.
Yeah, totally across the board. We are looking at absolute breakdowns in fine-grained control, severe temporal memory failures like that microwave incident, and a genuinely shocking statistical illusion regarding language prompts.
Right, where these models appear to understand text, but are actually just, experiencing severe mode collapse.
Exactly. So to really grasp the impact of what DexJoCo exposes, I think we need to look at how the industry has historically evaluated robotic policies.
Well, most benchmarks are still locked into testing with parallel grippers, those simple two-finger pinchers.
It's like testing a sports car exclusively on a straight, empty highway.
That's a perfect analogy. When you evaluate a multi-million parameter model on a basic pick-and-place task, it completely fails to stress test the high-dimensional continuous control required for actual human-level manipulation.
Right, because a multi-fingered hand, like the Allegro hand they used in this paper, has 16 degrees of freedom?
16, yeah. It has to roll objects, slip them between fingers, adjust grip strength dynamically.
And the tasks they designed to test those 16 degrees of freedom are brutal. They aren't just moving blocks around.
No, not at all. In the tool use category, the robot has to pick up a watering can and actually pour water onto a plant.
Right.
Or grab a hammer and strike a nail.
Wow. And the bimanual coordination tasks.
Those require two arms working together to assemble a peg into a moving tray. Plus, they have long horizon tasks like the microwave and reasoning tasks like a physical Tower of Hanoi puzzle.
Which brings up a big question. Are these MuJoCo tasks actually reflective of physical complexities? Or is this just a video game for AI?
It's incredibly rigorous. What makes this benchmark unforgiving is the physics engine underneath it. They leveraged MuJoCo's advanced soft contact models.
Because in older simulations, success was just, checking a bounding box. Like, did the object enter the target zone?
Exactly. But DexJoCo demands that 4 independent physical constraints are met simultaneously.
Let's break those constraints down, because calculating them is computationally heavy.
First, you have the object poses. The final position of the object has to be mathematically precise.
Right.
Second, articulated joint states. The simulation tracks the exact configuration of every single joint in the robot's hand.
To ensure it's forming an actual coherent grasp, not just magically levitating the object because of a physics glitch.
Precisely. Third, and this is the most computationally expensive one, contact conditions. MuJoCo is continuously resolving normal and frictional forces across dozens of contact points.
So if the fingers clip through the object like a ghost, the run fails.
Yep, automatic failure. And finally, temporal sequencing. The steps must happen in a logical physical order. You can't just skip step 2.
Which brings us to a massive logistical problem. If you are enforcing strict temporal and physical constraints, you can't just script these movements.
No, you need flawless human demonstration data to train the models in the first place.
But traditionally, getting 1.1K trajectories of human dexterity requires an impossibly expensive multi-camera teleoperation rig. How did the KCA and SJTU researchers pull this off without a massive lab budget?
They bypassed the visual occlusion problem entirely by moving to wearables.
Because multi-camera setups struggle with occlusion, right?
Exactly. The moment you make a fist or wrap your hand around a tool, the cameras lose sight of your fingertips. It's a nightmare for tracking.
So what did they use instead?
They used Rococo's heart gloves. These rely on IMU's inertial measurement units to capture continuous hand pose data regardless of visual obstruction.
That's smart.
Yeah, and then to capture the gross 60 spatial movement of the wrist and control the front arm itself, they just strapped a standard HTC Vive tracker onto this setup.
Okay, wait, I'm stuck on the Rococo gloves. A human hand and an Allegro robotic hand are physically completely different.
Very different, yeah.
The human hand has 21 joints. The Allegro has 16. If I make a fist in a smart glove, how does the system know what that translates to in the robot's hardware? You can't just copy-paste the coordinates.
That is the core of the retargeting problem, and it's where the authors introduced a really elegant software pipeline.
Oh.
They built a custom retargeting multi-layer perceptron, an MLP specifically trained to map the kinematic chain of a human hand into the constraints of the Allegro hand.
And how do they train that?
They designed a custom loss function that balances 5 competing physical priorities simultaneously.
Okay, instead of walking through the raw variables of that equation, let's translate what those 5 penalties are actually forcing the neural net to do.
Sure. So the primary baseline is preserving motion direction. If the human operator pushes a finger forward, the robot finger must advance. It maps the intent.
Makes sense. But they layer on additional mathematical penalties.
Right, like the cover penalty. This forces the robot to utilize its full physical workspace, preventing it from curling up into a cramped, suboptimal pose.
And there's a penalty for sensitivity, right, to keep it flat.
Yeah, that ensures sensitivity remains uniform across all digits, so your index finger doesn't wildly overreact while the thumb stays rigid.
I see. And the pinch behavior is uniquely isolated in this loss function too, because mathematically, a pinch is incredibly unstable to simulate.
Oh, it's so unstable. It requires 2 independent fingertips to converge precisely at a point in 3D space. So the loss function applies a massive penalty if the model fails to replicate the physical mechanics of a human pinch.
And the final one is collision. I assume naive retargeting often results in the robot's fingers just phasing through one another.
Exactly. This term heavily punishes the model if the simulated finger meshes intersect.
There's also a clever trick they use regarding latency, right? When you're teleoperating a robot, even a tiny delay makes it impossible to perform dexterous tasks.
Oh yeah, 100 milliseconds of lag and the operator gets frustrated and the data gets sloppy.
So how do they achieve real-time performance?
They don't calculate the kinematics for every single knuckle and phalanx. They only map the human fingertip position to the robot fingertip position.
And they let the inverse kinematics engine fill in the rest of the finger joint.
Exactly. It slashes the computational overhead and keeps the operator perfectly in sync with the hardware.
So collecting those 1.1K flawless trajectories is only half the battle. The real nightmare for ML engineers is figuring out how to actually feed that data into massive VLA models during deployment.
Right, without the robot moving like a stop-motion puppet. To test models like ACT, diffusion policy, and Pi 0.5, they had to solve the inference latency bottleneck.
Because in a typical synchronous control loop, the robot takes a picture, runs the massive model, computes a sequence of future actions, an action chunk executes that entire chunk, and then completely stops.
It just freezes to compute the next one.
Yeah, it's like a chef in a kitchen, chopping an onion, then standing perfectly still for 5 seconds to calculate what to do with the garlic.
That's a great way to put it. You don't wait for one vegetable to finish before you start the next. So to keep the robot moving continuously, they utilize an asynchronous inference mechanism inspired by the small VLA architecture.
So the next action chunk is being generated in the background while the current chunk is still physically executing.
Yes. And because these prediction windows overlap in time, they use a technique called temporal ensembling.
Meaning they take the overlapping predictions for a given time step and average them out to smooth the trajectory.
Exactly. It acts as a low-pass filter for the robot's intent, preventing sudden, jerky corrections.
But this benchmark reveals a harsh truth about deployment, doesn't it? Inference frequency is paramount.
It really is. Heavy models that take too long to compute their chunks suffer drastically. Lighter, highly optimized policies that run faster actually perform better in dexterous tasks.
Because they minimize the blind spots. Like when an object slips from a robotic hand, the contact dynamics change in milliseconds.
Right. A faster model utilizes the absolute most recent state observations to react. A slow model is still executing a pre-planned trajectory based on stale visual data.
Okay, let's dive into the evaluation data. They ran 550 trials across these models. What did the results actually reveal about the state of our architectures?
Well, we can start with a bright spot regarding robustness. They subjected these policies to severe domain randomizations.
Like what kind of randomizations?
Randomly altering the joint friction of the robot, the physical stiffness of the objects, the object mass, camera lighting, things like that.
And how'd the models hold up?
Under that stress test, the Pi 0.5 model showed incredible resilience. It significantly outperformed the transformer-based diffusion policy, DPT.
What exactly makes Pi 0.5 survive that kind of physical randomization when the transformer policy breaks down?
It comes down to how Pi 0.5 leverages pre-training. It utilizes a flow-matching architecture, but crucially, the authors retained the pre-trained weights in its action head during fine-tuning.
Oh, I see. So that pre-trained prior provides a massive foundational understanding of basic motor control.
Precisely. When the physics of the environment get noisy, like an object suddenly being twice as heavy, that deep pre-trained motor representation prevents the policy from collapsing.
Whereas the DPT model lacks that.
Yeah, DPT often relies on learning the motor mapping closer to scratch for a specific task, so it lacks that foundational anchor and quickly drifts out of distribution.
That's a great sign for the viability of foundation models in robotics. But unfortunately, the failures exposed by DexJoCo are much more concerning than the successes.
They really are. The first critical bottleneck is fine-grained semantic interaction.
The unlock iPad and photograph tasks highlight this perfectly, right?
Yeah. The models are actually quite good at gross navigation. They successfully pilot the arm to the iPad and pick it up. But when they are required to physically press the tiny unlock buttons on the screen, they completely fail.
So the vision encoders perceive the iPad's general geometry. They know it's a flat rectangle, but they are functionally blind to the interactive elements.
Right. They don't understand that a button is a separate, manipulable entity from the tablet itself.
We also see this lack of micro-adjustment in the insertion tasks. Like in the assembly task in the Tower of Hanoi, they get the peg right to the edge of the hole.
But they lack the tactile-like reactivity to wiggle it and smoothly slide it in.
Wow. But the most alarming failure mode, by a wide margin, is the breakdown in temporal memory. This is what we mentioned at the very beginning of the deep dive with the microwave.
Yeah, that one is wild.
Walk us through the mechanics of that failure. Why does the contextual memory of these massive VLA models just evaporate in long horizon physical spaces?
Well, in the microwave task, the policy successfully navigates to the appliance, opens the door, and places the hot dog inside.
Okay, so far so good.
But at that exact moment, the visual observation looks incredibly similar to the frame right before it released the hot dog.
Oh, because the robot just sees its own hand right next to a hot dog.
Exactly. And the dominant training prior for a hand hovering near a hot dog is grasp the object.
So even with observation histories and temporal ensembling, these models completely fail to maintain a coherent, high-level state machine.
They really do. They lack an episodic memory module that securely logs, step 2 is complete, we are now executing step 3.
So without that hard internal state transition, the model just reacts to the immediate visual stimuli. It falls back on its strongest statistical prior, grabs the hot dog, and pulls it out.
Right. It's a devastating flaw for any practical deployment.
Which perfectly sets up what is, frankly, the most fascinating and concerning finding in the entire paper, the language generalization experiment.
Yeah, this was the moment that really recontextualized how I view current VLA research.
They tested the Pi 0.5 model on the unlock iPad task specifically to see if the language part of vision language action was actually working, right?
Correct. And the setup for the test is simple. During training, the model was fed text prompts to press single digits on the iPad screen, numbers 1 through 5.
Okay, and for the evaluation?
For the evaluation, they threw completely unseen language prompts at it, like the word 2 spelled out with letters, or the mathematical equation 1 + 1.
And if you just skim the top-line evaluation metrics, it looks like a massive win. When prompted with the spelled-out word 2, the model successfully pressed the number 2 on the screen roughly 30% of the time.
Which sounds great, right?
Yeah, you could easily look at that and publish a paper saying the VLA successfully reasoned that TWO maps to the semantic concept of 2 and generalized a physical action.
But when the authors plotted the output distribution on a heat map, the illusion completely shattered.
The model wasn't reasoning about language at all.
Not even a little bit. It was experiencing severe mode collapse. The heat map revealed that regardless of what text instruction you fed into the model, it stubbornly outputted the physical coordinates to press the number 2 about 30% of the time.
And the number 3 about 30% of the time.
Yep. It had just developed a hard bias for the center of the screen.
So it was just blindly guessing 2 or 3. And the fact that it hit 30% of the time was just a statistical coincidence.
To definitively prove this, they ran a control test. They prompted the model with a digit it had seen during training, the number 4.
And if the model understood the language prompt, it should navigate to 4.
Right. But instead, the precision tanked to an abysmal 4%.
Wait, really? 4%?
Yes, because even when explicitly told to hit a target it knew, the model's action head ignored the language embedding and just randomly defaulted back to pressing 2 or 3.
That is incredible. The statistical math the authors provide here is damning, and I think it's worth translating for the ML engineers listening.
Go for it.
They ran tests to see if the language input affected the physical output. While a basic chi-square test technically showed that the output shifted slightly when the text changed, the normalized mutual information, the NMI, between the text prompt and the physical action was 0.018.
Meaning the overlap in actual useful information between what you told the robot to do and what it physically decided to do was practically 0.
They also calculated the Jensen-Shannon divergence across the different instruction pairs. JS divergence essentially measures how much the model's behavioral distribution shifts when you change the input.
Yeah, and what was it?
The divergence was averaging 0.026.
Wow.
It was practically flat. The action distribution did not care what the language prompt said.
So the model is treating your complex language instruction as light statistical noise, ignoring it, and falling back on a hard-coded physical bias.
Exactly, which forces us to look at DexJoCo not just as a new leaderboard for researchers to chase high scores on, but as a critical diagnostic tool.
It proves that simply scaling up data parameters isn't enough. Our current VLA architectures are hitting a structural wall.
Yeah, they can survive visual noise, but they are failing at fine-grained semantic interaction.
They are failing to maintain episodic memory over long horizons.
And they are completely failing at true, physically grounded language conditioning.
And that leaves us with a highly provocative question to consider as you look at your own models.
What's that?
We have spent years scaling up the vision encoders and the language parameters of these massive architectures. But if a state-of-the-art VLA experiences total mode collapse when asked to translate a simple language concept into a precise physical coordinate, are we fundamentally missing a bridge?
It heavily implies that the action part of vision language action models is currently just along for the ride.
Operating completely disconnected from the deep semantic reasoning of the large language model. You can't just plug an LLM into a robotic controller and expect true embodied intelligence.
The representation of language and the continuous physics of action are basically speaking two entirely different mathematical languages right now.
And solving that translation is the next frontier.
And that is exactly where the research needs to pivot. Thank you for joining us for this deep dive into the source material. Keep building, keep questioning the benchmarks, and we'll catch you on the next AI paper slot.